Okay, so if you look at homework 2, question number 1D, I say find the average value of V left. Not a problem. Now let's go on and read this brilliant part I have for part E. I basically asked you to find V left. I give you the hint, think. And you could say, well, yeah, I'm going to take this crazy value here and copy it here because I thought. Okay, I do a lot of cutting and pasting and things. This should not be left. This should be right. And there's no work involved.
Weekly. Oh,
Okay,
I do not have that.
that's a free bill. Okay, so so that's just to when you go over to. The other thing, well, you have to, there's a way to figure it out. The other thing is, probably not, this doesn't have to get the 2 sections the same. I'm not gonna get quite to the point where you're ready to do daily homework 3, which is due on Friday. So this is gonna be due on Monday instead. Okay? And the other kind of, just, housekeeping details. Tomorrow they're predicting some level of ice storm or ice covering, or it's not quite clear. Chances are if there's ice, even if it's a small, I most likely, unless it all melts away relatively soon, I most likely won't be in tomorrow. So if you try tracking me down tomorrow, I'm not gonna mess with ice. No, that's having driven on a couple of times. No way. I'm just completely staying away from that. Actually, this service I think is supposed to be relatively bad for it. Not messing with ice. Okay, let's go back to our problem. Okay, so we have this U. We don't have U at all. We have V. We have a 2-state problem. This is plus epsilon, and this is minus epsilon. And we wanted to find U. Okay. And how do we find U? Done. Okay. It's diabolically simple.
Minus partial.
I guess this is minus partial.
The natural
Natural log of Z, which is the
precision
function with respect to
beta.
beta. What is beta?
One, no?
1 over QBT. Okay. So we do that. And how do we define zeta? I'm sorry, not at all. How do we find Z?
Sum of all microstates.
So on all the microstates I,
And
e to the minus
beta.
beta.
To
Yeah. I'm just trying to write in 1 over KBT, so I'm just calling it beta. In this case here, how many microstates do we have in a 2-state system? 2. Okay. It's wild. So this is going to be e to the minus beta minus epsilon plus e to the minus beta plus epsilon. So this is our e to the beta epsilon. This e to the minus beta epsilon, and we stated that that is how many Kashas?
2.
Twice Kash. Actually, a former student gave me action figure of Kosh. I can bring in the action figure of Kosh.
I forgot that that's a character from somewhere.
That one five.
Oh,
That one brilliant science fiction.
You have to do the voice.
We're all Kosh. Use the closed circle. Who are you? Never ask what you want. Shadows ask what you want. Borlons ask, who are you? Makes a big difference.
Who's Kosh?
We're all Kosh.
Okay, got it.
Because Kosh gets killed and he's replaced with Kosh. We're all Kosh.
Wow. Circle.
What? We can all come back. Full circle. Okay, so what is U on this? So U minus partial with respect to beta of the Ln of we're all Kosh.
2.
Oh, the 2. I want to do a little review of hyperbolic functions after this.
Something over the 2 columns.
Yes.
Okay, so if
One
we put in
over
more
2
details.
Kosh.
Okay, so what goes in the bottom of the logarithm? the 2 times cosh. Right, epsilon.
Epsilon. Upstairs, a 2 epsilon, but I don't know.
Okay, what's the derivative of cosh?
Minus, or no, I don't remember.
Plus or minus? We're gonna prove it a little bit.
I mean, if you move a little bit, it would be easier. Right, so. Plus.
Then here times
Epsilon.
epsilon. Okay, sinh over cosh is
Tangent.
hyperbolic tangent. You get this minus epsilon hyperbolic tangent. Epsilon. We're gonna look at what that means. This will make perfect sense. The other thing is, we can also now, we can find CV. So let's do a little view of this. So any heat capacity is defined to be what? Any heat capacity at constant x.
Changing, heat.
Okay, so it's a change in heat, dq over
Changing temperature.
change in temperature with some constant x. Now there's going to be something called a molar heat capacity. And so this one here, this is going to depend upon the size of the system, what this would be. Suppose I want a heat capacity that doesn't depend on the size of the system. What you need to do is divide by the size of the system. So what might be a good measure of the size of the system for a molar heat capacity?
A mole.
The number of moles in the sample. And so what we can do, we can define the molar heat capacity as 1 over n dq dt at constant x. And some physics books are kind of notorious on this. Sometimes they'll mean this and just call it heat capacity. Sometimes they'll then sometimes switch back and forth between the two. So just be aware that sometimes you have both of these here, and authors can go from one to the other and really not sometimes be consistent. I've seen that a lot. Drives me nuts, but it's just the way it is. Okay. Now, in our case, what are the 2 most common forms of x?
B and B.
V and P. So if I want this one here, what does this become?
Which one of the CVs are we talking about?
Constant volume.
Mahler one or no?
We had this one.
DU and DT.
This is going to become du dt.
Pressure constant.
Now let's go through the argument again. Prove it. Everything you said is true.
Volume constant, so dV is 0, and so from first law,
So we have du equals dq, and then minus the work right as pdv. And then this right here is 0 if v is constant. So you get du equals dq. I put it in there, and that gives me this. Okay. So what is CV? V epsilon hyperbolic tangent. Here. I'll be nice and I'll pull out. There's a minus sign here too. Minus sign. I'll pull out the minus epsilon.
that's so.
It's like I did it for you.
Are there hyperbolic secants squared?
It turns out there are. So what might be a good candidate then for this?
Hyperbolic secant
A
squared.
hyperbolic secant squared, right? What's the derivative of the tangent?
Secant squared.
Secant squared, and this is a hyperbolic secant.
What an amazing realm of unnecessary measure.
Okay. Now, what do we have to do now? What's the most important thing you learn in Calc 1?
So we'll take a derivative of the inside.
Or take the derivative of the inside. So rainbow, right?
Oh.
So it's this.
Yeah.
Here. I'll be nice and pull out the epsilon.
How could I forget the school?
You think you're ready for graduate school?
I'm not, apparently not after this.
Okay, so what is beta?
Then what?
What is beta? Because we're going to temperature dependent.
Over KBT.
So this is going to be KBT to minus 1 power.
So it would be minus minus KB over T squared.
So I'm gonna pull up the KBs, but remember the KBs in the bottom. This CV is
Oh, yeah,
gonna
that's
be minus epsilon squared over KB. Hyperbolic secant. Okay. Then what is T to the minus one power?
I love how you ask these questions. When you say something and you mean something else, but we know what you mean. It's minus 1 over T squared.
So what do we get here? We get our CV. It's epsilon squared, KB T squared. Hyperbolic secant. Boom. Which is what we'd have guessed. Kidding. But what's the important thing here? We went from microscopic physics, we went from that two-state system, and we're actually able to calculate macroscopic quantities. I mean, the statistical mechanics is really a slim jam. I mean, once you get it, you can really do very, very good results. Yes.
How do you go from du or dt to d whatever over d?
Okay, because
Due to the limited Bourdon law.
Oh, okay.
I have no idea why I
Yeah,
haven't made it here.
I
Okay.
was like,
Well, you should yell at me for that, saying that doesn't make any sense.
well,
I fixed it here, but I did not put it there. Keep me honest. Okay. That make sense? Questions? Okay, so what I want to do is just a little review of just hyperbolic trig functions. The two areas where they come in quite a bit are statistical mechanics, hyperbolic trig functions. Then the other one is also if you do a lot with relativity and stuff. They actually come in with relativity a fair amount, more than you think that they would come in. I mean, they come in other spots too, assuming classical mechanics and there are other things. But primarily, you're going to see them in those two areas, just probably the most.
Where is it in relativity?
Well, we're gonna get, when we get to the, I'll mention it when we get to, once I actually talk about hyperbolic tangents and that, because it comes to there.
Or I think I remember it was a bunch of weird approximations.
This one is an approximation, it's an exact thing. Okay, so what we can do here is let's do a brief review. Hyperbolic trig functions. Okay, so I'm gonna have you drive the run. I'm just gonna set it as a fact. What do you know about e to the ix?
cosine ix.
Cosine,
Two ix.
cosine,
Just X.
Cosine
x,
I sin it.
cosine x. Okay, so if I have e to the minus ix, right? I replace this x with a minus x, and that would then become cosine of minus x is
Cosine of it.
cosine of x. And if I take sine of x and put write it as sine of minus x, this is sine of minus x is
Sin.
it becomes minus I. Okay. Add these two together. I get e to the ix, and c to the minus ix equals 2 times cosine of x. So your cosine of x is e to the ix, and c to the minus ix, all over 2.
And the Euler relations are just from the Taylor expansion of these. Alright.
Now, somebody could say, well, it's a little bit of a cheat because you never proved that the Taylor expansion of a complex function is that same form. And I say, yeah. Okay.
Whatever.
Okay. This is why you can't really be a mathematician. There's some things I don't mind showing, and others I was like, really? We had to do that.
But like, is it? I mean, it is because we get this relation. Is there proof for that?
Well, you have to go through and you have to show that you get the same result when you do it for complex functions, and you do. And then it all falls through that.
Okay, got it.
Although the mathematicians will sometimes have another, there's sometimes what they define and just, it just drives me nuts. So we have this. Now the question is, what is the cosine of ix? So instead of having an x, I'm gonna put an ix in here. So what would I have? We're using this little recipe, I get e to the I, ix. Plus e to the minus I, ix. All over 2. So this is what? This is e to the minus x plus e to the x. 2, and we define this formally to be hyperbolic cosine x. That makes sense? And if I were to make a graph of this, what would it look like? So first of all, if x equals 0, what do you have?
1.
Well, 0 here, 0 here, that would give you 1 plus 1, 2 over 2. This is a 1. Now, as x gets really, really large, this term goes to 0. And what does this term do? It blows up. Yeah. So this is going to go up like this. Okay. Now, if I go to very, very large negative values, if I have e to the minus x, that goes up to something big. And e to the minus x goes to 0. So this is going to go like this. What we have here is that your cosine of minus x is if I put a minus x, so this is going to be the cosine of x. Am I over in general solid line? Okay. So a mathematician would call this a, if you have f of minus x,
An even function.
Yeah. Equals f of x. This is an even function. Okay. Well, what I could also do is I could come over here and I could subtract these two. If I subtract the two, you can see that these are canceled and these two add. That, and I can write this as I sine of x. Equals e to the ix, and it's e to the minus x. Over 2. Okay. And then I can do the same thing. I can replace x with ix. Then I sine ix equals e to the ix, I of x. So what is this? This is e to the minus x minus e to the x. 2. I'm going to pull out a minus sign here. And put it like this. And we formally define that to be this h.
So e to the x or e to the.
Oh, there should be an I in here.
E to the minus x is cosh plus sinh.
Yeah, you can actually, if you wanted to, you could actually then figure out how to write then kashas and sinches in terms of e to the x. Just like how you do this.
Yeah.
You can do the exact same thing for e to the x and e to the minus x in terms of kashas and sinch. And you do that sometimes. Yeah. So if we look at this, if we graph this guy. Okay, what happens at x equals 0? You hit 0. And this is 0. And then what happens? As x increases here, this goes to 0 and this blows up. So this goes like that. And what happens if I go to minus x, really large minus x? And this one decreases, this explodes, but there's a minus sign in here. And this is going to go like this. What it's going to have here is that the sign, I'm sorry, the sinh of minus x is minus the sinh of x. In other words, f of minus x minus f of x. And a mathematician would call this an odd function. So why is the derivative of cosh sinh? take the derivative of this, what happens? This pulls in the minus sign. This stays the same. So if this pulls in the minus sign, that's exactly so. Okay, what's the most common mistake if you take the derivative of a cost?
Minus sign.
You put a minus sign in front. That doesn't work. Now, if you just have regular trig functions, what's the dumb way to remember the minus signs?
I remember it in a smart way.
Okay, I'm gonna give you the dumb way to remember it. I've never actually forgotten it. If I'm gonna take the derivative of anything with the word co in front of it, you get a minus sign. So cosine, minus sign comes in. Cosecant, you get a minus sign there. Cotangent, minus sign. That's the dumb way to remember the minus sign. But it only works for the normal trig functions, not the hyperbolic stuff. Okay.
And if you take a derivative of sinh, or you live, you get cosh.
Exactly.
Amazing.
So, what's one way to define a tangent?
Sine over cosine.
So sine over cosine. So how do you think you're going to define a hyperbolic tangent?
Sinh over cosh.
Yeah. So sinh over cosh. So we're going to define a hyperbolic tangent. To be the sinh. An analogy with regular trig. If you look at them, if you were to put these two graphs on top of each other, this is cosh. This is sinh. Let's see that before. This is cosh. I'm sorry. Yeah, let's see. Did you get it or did I work up?
No, I need you asking. I need that.
Okay, so what happens here if I then plot this? For really, really large values of x here, these two functions are the same. So for large values of x here, what do you get? One. You get a 1. If here's 1. That. Then for x equals 0, you get a 0 there. So this is going to look like one of this. But what's going to happen on the other side? Yeah, they both go to the same thing, but one positive version of it and the other a negative version of it. Okay, so this is going to be. Okay. So now let's plot. Can this go?
Yep.
Okay. So now if we plot our u versus beta.
Beta versus t.
No, I want beta. This is going to be plus epsilon. And this is minus epsilon. Remember that this is going into minus epsilon. Hyperbolic tangent of epsilon. This is going to look like this. Okay, now what am I going to do with this part of the curve here? I'm going to kill it. How come?
Negative temperature.
Yeah, it turns out those negative temperatures aren't very popular these days. Okay, so we're going to get rid of these. This is negative temperature. So ignore negative temperature. Okay. Now on this graph, if I were to say point out where is hot and where is cold, where is hot and where is cold?
Close to 0 is hot. Close to infinity is.
This is hot. This is cold. Remember, this is 1 over kBT. So if this is a small value here, 1 over small is big. This is large values. I'm plotting this versus big. Whereas here, if I have a 0 here, I can get a 0 there. I can have a really, really large. Now remember, here's our system. It looks like this. So what did we say happened? Where are you going to find the system if you have something cold?
Get the ground state.
It's going to be here like that. So you're going to be in this state here. So if you're cold over here, you're going to have a value here of this is minus epsilon. You're going to get a value minus epsilon. Now, what did we say happens to the probabilities as the temperature increases?
They all become.
They all become equal. So if you're at a really, really high temperature, are you gonna find the particle here or find the particle here? Equally likely. Well, this is minus epsilon, this is positive epsilon, the average is gonna be. So this is making absolutely perfect sense. So we're gonna get short. That makes sense? Kind of a neat little thing. Questions? Okay, so what I want to do next is I want to pull in the idea of enthalpy. In order to pull in the idea of enthalpy, I think properly, you really need to talk about what it means to be a Legendre transformation. And so I want to talk about enthalpy and Legendre transformation. And what you're going to do is on the little homework here, you're going to do your own little Legendre transformation on the Helmholtz free energy. But this will be due on Monday instead of Wednesday. So, I'll talk about enthalpy. And Legendre transformation. Okay, and let's just do a little, this is gonna be why. So, one of the really important experimental techniques in glass is something called DSC. And what does DSC stand for? Differential
scanning
calorimetry. So what does that give you?
Difference, heat flow.
Okay, sure, but I mean, what do you get from it? All that's true. I'll see how it was.
So like
heat.
the result?
It's gonna give you,
No, that's not the one. The heat capacity, you're thinking photometry.
Okay.
You can get heat capacity, crystallization temperatures, glass transition temperature.
okay, so what's one of the first ones that you get is really gonna be heat capacity. What kind of heat capacity? It's gonna be really heat capacity at constant pressure.
Yeah.
And it's gonna be really connected, actually, it's gonna be a way of actually measuring the enthalpy of the system. And so that differential calorimeter is a way of getting the enthalpy of the system, and then from that, we can also then figure out, well, they're actually, the two are connected. How you're gonna then get actually the heat capacity at constant pressure. And so this is why we're gonna start looking at enthalpy, because one of the common things we're gonna look at for an important experimental technique is DSC. And it's also gonna tie into the entropy of glass, because people are gonna use this to get the entropy of glass. And I wanna basically show you how this works so that I can shoot down there. Okay, say no, but you're gonna see people do this all the time. So this is why we're doing this. Okay, so let's go through and do this. So before we look, Legendre.
LEGENDRE.
Yeah. That's actually spelled correctly. Okay. So before we look.
But even if it wasn't.
Yeah.
We
No
don't
one,
discuss-
okay, I just, oh, you probably speak French, right? Really? Being from Vietnam, no French?
No,
Okay, I just.
I mean, they did colonize us, but no.
Okay, because my friends who I've had, because you're not the first person from Vietnam I know, and they all spoke French. Okay. So, well, they did. They just. Okay. So, but it's spelled correctly.
Yep.
Okay, so before we look at entropy, we need to understand what Legendre transformation is. So let's say we have a function here of x and y. And what I want to do is I'm going to define a new variable. So we define a new variable u as, let's say u is by definition The partial of f with respect to y. Okay? That's just how I'm defining it. So what we're gonna ask then is, I want to create a new function g. So we want a new function g, which only depends on x and u. Okay, we want no y dependence. The question is, how do you do this?
And
Okay.
no explicit y depends, because you can depend on y, right?
Well, it is, but when we do it again, it's all gonna come from the differentials that we're gonna look at. The differentials will tell the dependency. Okay. So the way we're gonna do this is we're gonna define this function here, this g. We're gonna climb it through this, and the claim is that this is gonna be by definition. What you do is you take the variable you want. So what variable do we want? Okay, what new variable do we want? I'm sorry. We take the new variable that we want, which is u. This is the new variable. And then we multiply this by the variable we want to get rid of. So which one do we want to get rid of? Y. Well, this right here, this is the variable we want to remove. Okay, then we're going to subtract the original. The claim is that this is going to give a function. So the claim is that this g here will only depend on x and u. Okay. This is called a Legendre transformation. And all those thermodynamics functions, the enthalpy, the Helmholtz free energy, the Gibbs free energy, they are nothing but examples of Legendre transformation. I don't know if any of you, I don't think any of you had the classical mechanics course. Classical mechanics, one thing that you basically find out how to write F equal ma in a very, very abstract form. It's called Lagrangians. And what you do is that if you do a Legendre transformation on a Lagrangian, you get a Hamiltonian. So a Hamiltonian is really nothing but a Legendre transformation.
So Hamiltonian is just that F equals ma?
In a very, very abstract form. It's more like dPdt.
Oh,
The Hamiltonian is often just the kinetic energy plus potential. It doesn't have to.
yeah, I don't remember if we ever, I think that the girl promised us to show us the case where it's not, but I have never seen it.
It depends on basically how your velocity is going, whether it's quadratic in position. If it exceeds that, it turns out that it will not. And also whether there's a time dependence. And
I should listen to a whole other topic.
it's a beautiful concept. It's really, it's one of those things. Classical mechanics is really, it's basically chamber music. You know, it's just you're listening to it and you realize you're just listening to beauty. And that's what that whole course is. You look at it and it's just beauty. It's just the entire subject. And it often gets poo-pooed as it's classical and you quantum. Well, you don't understand. You don't just take beauty and throw it away because you don't understand. Okay, so let's prove this. So in order to really show the dependence on something, what do we say we have to look at?
Exactly.
The differentials. So we have to look at dg. So look at dg. All right, dg here. So what do we know about dg?
Actually, over the right.
Okay, I agree. So what is it? This term is? What's the differential of this?
Du y.
duy. So this is
This
du, and I'll put a little parenthesis here, y plus udy minus
Yeah.
df. Hey, do we know how to write df? I think we do. Okay. I'm going to put this y out. So this is y du. It's u dy minus, and you tell me what to put in for df. Remember, df depends on x, it depends on y, so it's
X dx. Partial.
partial f with
with
respect to
X.
x dx. So this is how much f changes if you only change x, plus
Partial of f with respect to y.
partial of f with respect to y dy. So this is how much f changes if you only change y there. Does this have a name? Partial of f with respect to y. That's our new buddy, u. Okay, so what happens? That term here cancels that term here. So this gives me y du minus the partial of f with respect to x. Half here is that we have the variation is occurring in u, variation is occurring in x, which is what we wanted. Okay. Now let's apply this to enthalpy, because enthalpy is going to be nothing but this. And all the thermodynamic functions are all just variations on this. And then the class is going to end abruptly because basically this is how far I got with the other one. We're gonna have time over.
We always do.
That's what happens. The class gets bigger, the class gets smaller. It's just the nature of teaching. From teacher, you'll find out. Okay, what are we doing? We're doing the following. Okay, so apply to thermodynamics. Okay, so we have our du, and what do we know about du? Yes. And I know, but you have to keep on writing it. Okay, that's, I have to give you the same joke that I did in the morning. Okay? So the TDS, I know, but you have to keep on writing it. 'Cause it's TDS. TDS.
Oh.
Sorry, I won't work as hard for the other jokes. Okay, so then minus, and then the work becomes PdV. So we have the ds here, we have the dv here. That means we can say that then u is s, function of s and v. And so what can we do then?
Get rid of v.
Okay, well, we can write the u. We're gonna need this in just a bit. The du is going to be partial of u with respect to s ds. And the partial of u with respect to v dv. And then we match this up to here. So this gives us t is partial of u with respect to s. And then here's v, the third line there. That means that this has to be this. So that means that minus p is partial u with respect to v. Yeah, we already did it last time, but I needed these out again. And plus, it never hurts to see. So we want a new function here. We want a new function h, which depends on s, the entropy still. Okay, and p. Now, then what? Remember what we had here. Remember we had this g is this u y minus f. What did we say this u is? This u was
Partial of
partial of f with respect to y. Okay, so what do we want to do? This depends on s and v. And we have this new function, which is defined as the derivative of this guy here with a minus sign here. Okay, and so it's the same thing as basically what we have over here, just with a minus sign. And so what I want to do is I want to get rid of the v because of p. That make sense? So we want to eliminate v in place. Now, so I'm gonna have my H, I'm gonna do a Legendre transformation here. So what are we gonna do? Now, since there's a minus sign here. Okay, right, when I define this here, I could just as well put a minus sign here and make this a plus, and I could have still had the same functional dependence. In this case here, since my P here, which is this derivative term is coming in with the minus sign, I'm not gonna need another minus sign. Because that's kind of built into there. So what do I want to get rid of? Or what do I want? I want P. Then what variable do we want to get rid of? V. And then what do I have to do? So this is intrinsically has a minus sign from over there. So instead of having a minus U, I'm gonna have a plus U here. Because that minus sign's been built in because of this stupid minus sign over here. Okay, so up here, I could just as well put a minus sign here, maybe there's a plus and get the same answer.
Yeah.
Modules of signs, it would be this independence here. And so what I'm doing here. Yeah. Does that make sense? And then the claim is that this is going to be a function of just S. Okay. And so how are we going to do that?
Open check that it is,
Yeah, how are we going to check it?
take an exact differential.
Take the exact
I mean,
differential.
Legendre transformation by default will give us that.
Yeah, but I mean, we always have to verify. Then we want to get a couple other results because what I'm going to show you. Again, I didn't do this, so this brand new knowledge for you guys. We're going to show that CP. Right, which is going to be this. It's also going to become EH.
What do you think?
Yeah. Okay.
We had thermal one,
Okay.
did all of those.
Okay. And so the DSC is going to give us this, and from that we can also then get H. Okay. And then from tinkering with this too, we're then going to figure out how to do this to actually calculate the entropy of our system. And then people are going to then apply this to a glass and say, see, residual entropy of a glass. Violation of the third law of thermodynamics. And we will look at them and say, moron. Okay. But we're not there yet. But that's where this is going. Okay. Okay. So we actually will be learning some glass stuff. So we could say, I like all this stat Mac. It'd be really nice to actually get glass, and of course called the physics of glass. And this would then tie back into that part there. Okay. But that'll be Friday. Okay, every day.